Okay, so good morning, good afternoon, everyone. Today is an exciting lecture, and we're going to start a new chapter, which we will hopefully finish today. Okay, so it'll be very short, but as I've gotten you accustomed to, there's a story that we're going to start with. So we're going to dim the lights first. Actually, we'll just turn them off. Okay, it's mood lighting. Okay. And we're gonna put some music, okay? Okay. So I want you to focus with me on this new topic that we're gonna be talking about today. So once upon a time, there was a king from Bavaria who was good at math and wanted to calculate the area of a land he hath. So he drew up and measured the perimeter of his plantation, but none of the methods he treasured could help with his calculation. So you see, the land had an odd outline that looked like a dromedary. With sides so flat and inline, one could only grow raspberry. I don't know why, but you could only grow raspberry on straight lines. And days had passed to no avail, our king's formulas were doomed to fail. Then, while throwing his work in his diaper pail, he soon found the Holy Grail. He drew up a series of rectangles across the entire land and lined them up at right angles and added their areas by hand. He rejoiced at this feat, for this was an annoying thorn, and instead of it being a defeat, the science of quadrature was born. All right. So, let's get to myself. Okay. So, you probably have guessed that quadrature actually means numerical integration. It's a synonym for numerical integration. And historically, there is truth to this story. There's historical truth to this story. The Greeks, the Babylonians, and the Romans, they've used quadrature to calculate surface areas. That's how integration was born. And the word quadrature comes from using quadrilateral elements. These are squares or rectangles. They're quads. And they would put up these quads under a curve to calculate a total surface area. Okay. The learning objectives for this chapter are listed here. So again, to remind you, these learning objectives you will be held accountable for. So in a way, these are going to be part of your study guide for the exams. Okay? We did this with regression, and now we're doing this with numerical integration. At the end of this chapter, you should, and hopefully you will be able to, define what quadrature and numerical integration means, calculate the area under an analytical function using what we call Newton quotes formulas, calculate the area under a discrete set of data points using Newton quotes formulas as well, use the left point, right point, midpoint, trapezoidal, and Simpson's 1/3 and 3/8 rules. We will learn about all of these rules to calculate the integral of a function or a discrete set of data points, derive your own formula to approximate an integral, okay, and calculate the error bounds for the midpoint, trapezoidal, and Simpson's 1/3 rule. Okay. So as we introduced, the goal of numerical integration is to find the area under a curve. And typically, you are given a curve, whether that's specified analytically, like a function, sine x, for example, and you're asked to compute the integral of said function between a and b, or on the interval a and b. Okay? One of the most popular methods, and it's the one that we will focus on, is called Newton quotes integration formulas. And the idea is simple, is given a complex function f of x, assuming we don't know how to integrate that analytically, then the idea behind Newton quotes integration is to approximate f of x locally as a polynomial, and then integrate the polynomial analytically. We know how to fit a polynomial given a set of data points, right? We did that. That's interpolation. So that's what we're doing here. We're essentially taking interpolation. We're taking an interpolating polynomial. We're fitting it between 2 points, and we're integrating that polynomial. Okay. Now this comes in many flavors, right? The order of the polynomial is a big deal. We will start with the simplest polynomial, and that gives rise to what we call the midpoint rule. And the idea behind the midpoint rule is we approximate the function as a 0th order polynomial between a and b. In other words, we approximate the function as a constant on the entire interval. So we write f of x is equal to c, constant. And therefore, the integral of f of x between a and b becomes the integral of that constant, which essentially is nothing more than c times b minus a. The width of the interval times the height. Okay? Pardon me? Okay. So now the question is, how do you select this constant? There are numerous ways. The three most popular are given by what we call the left, right, and midpoint rules. Okay? So we start with the first way. It's called the left point rule, where we say we take the constant to be equal to the function value at a. So we assume that our function on the interval ab, it's equal to f of a. So this red line is going to be replaced essentially just by a horizontal line at the function value f of a. So what that does, it approximates the area under the curve by this rectangle. Okay? And the area of this rectangle is simply b minus a times f of a. That's called the left point rule, right? Now, obviously, in this case, we're committing an error, and that error is this difference, this gap over here between the rectangle and what we left off under the curve. We can also choose the constant to be equal to f of b, right? That's the right-hand side of that rectangle. And if you choose it in this way, then you get this area. So in this case, you're overestimating the curve, but that's not necessarily the case everywhere, right? But in this case, you overestimate the curve, but that's how you approximate this integral in this case. And then finally is the midpoint rule. You could say, well, you know, the left point in this case underestimates, the right point overestimates, and this could be set to pretty much any number of functions. Why don't we pick some point in the middle, the midpoint, okay? So then the midpoint rule does that. You choose the constant as being the function value at the midpoint, a plus b over 2. And that's your midpoint. And then you draw a rectangle based on that height. You still have b minus a as the width of the rectangle, but the height now is f of a plus b over 2. So while you overestimate on one end, you underestimate on the other, and the hope is that by choosing the midpoint, you kind of balance these two errors. And that's called the midpoint rule. It is the easiest and simplest way of doing an integral. Okay? Now we'll learn, in a little bit, we'll learn how to make this a little bit more accurate. However, the challenge here is that this requires a function value at the midpoint. And as we will see later, this is going to be problematic when we have a discrete set of data points. What if you do not have a value for the y data or for the function at midpoints between x1 and x2, for example? Okay? So then you cannot apply the midpoint rule. Okay. Now, I need you to download the following notebook. I don't know what happened. Go to your Canvas. Okay? Go to your Canvas. And obviously, this was not updated. I want you to go to your Canvas and download under notebooks. There is a notebook under quadrature, okay, called Quadrature with Gaps. So I want you to go ahead and download that. Give me a second here. I'm still synchronizing my my keynote over here. Okay. Okay, so if you have that downloaded, I want you to go ahead and open it up. And so where are your names? Where are the name tags? Come on, guys, don't lose the excitement.
There are a couple.
I know most of your names, but some of you I'm still kind of a bit, foggy. Okay? So for this first coding activity, you're going to download that notebook, and I want you to create a function for each one of those, the left point rule, the right point rule, and the midpoint rule. Okay, you're going to develop 3 codes, 3 functions, 3 routines that will take a function in and compute the integral using left point, midpoint, and right point rule. Okay, and I want you to calculate this integral on the interval a 0 to 1 of this function. Everything has been coded in for you except for the routines themselves. Okay, so go. You can work in groups. You got 1 minute. Let's see. So you'll notice the notebook structure has changed. I have things activity 1 and activity 2, activity 3, etc. And I'm going to go ahead and open up notebook over here. There's not much noise now. Later, there's going to be more discussion, okay? Stupid Google Drive didn't sync anything. Huh. Okay. All right, so let's see where you're at. I'm actually going to have to download it from Canvas myself because my Google Drive did not sync any of my files, unfortunately. So you should have this completed, hopefully. Let's see. So under Jupyter Notebooks, we got quadrature activities, and then we have download. Okay. Okay. So, all right, who's having trouble with this? It's pretty straightforward, right? Very straightforward. Were you able to apply it to the function? So what I have here, I define this function, call it my f. It returns 1 plus 0.5 sine 1.75 pi x squared. And I made this function as close as possible to to our king's piece of land, which was shaped like a dromedary. Okay, so you could plant your raspberries over here, and so calculating this area, and the left point rule, midpoint rule, and the right point rule is simply given. They're simply given by b minus a times f of a for the left point rule. For the right point rule, it's b minus a times f of b. And the last one is b minus a times f of a plus b over 2. Okay? Now, notice how I designed these functions. They take in an arbitrary Python function. So notice how I designed these routines. They take in any function as long as it's a Python function. And you give it a and b, the bounds for the integration and just gives you the integral. Obviously, this estimate is going to be pretty terrible, as we will see right here. So the left point rule gives you 1.0 because it uses this height for the entire rectangle, so it misses all the areas, these humps. And for the right point rule, it takes this point as the height, so it creates this rectangle over here. And for the midpoint rule, it's somewhere in between, takes this value, so it still misses quite a bit. So for reference, the true value, I'm going to use a function called integrate that I'll introduce to you later, my F01. The true value is 1.27. Okay, so the right point rule was interestingly very close to that value. Okay, now let's switch back to the slides. And now that I have my keynote, I'm hoping I got my keynote. So what happened, my keynote on my desktop did not synchronize properly with what I have here. Okay. So obviously now we used an entire interval, right? The entire interval A and B, and we approximated this huge function using this very wide interval. However, we can increase accuracy like our king did. Rather than taking one giant rectangle across the entire function, why don't we split that interval B minus A into smaller intervals and apply the midpoint rule or the left rule or the right rule to each one of those intervals. And this is depicted over here. Rather than just taking this entire interval as the one interval for the function, why don't we split it into smaller and smaller rectangles and apply the midpoint rule to these smaller rectangles? Don't you agree that this would give us a better estimation? Yeah, because then the rectangles would be they would not miss much of the curvature of the function, okay? So this is what we're going to do next, and that's going to be part of your activity 2. And you got 3 minutes for this one, but what I want you to do is take essentially the function that you just defined, and I want you to develop a Python code that computes the midpoint rule for an analytical function with an arbitrary number of segments, okay? An arbitrary number of intervals, okay? So go, and you should have some guideline code in there. So for activity 2, you kind of have this already defined for you. So you can apply this to the midpoint rule, left rule, right rule. Once you figure one of them out, the rest is easy. So I would start with the left rule. And notice now, the left rule takes a function f, takes the interval a and b, and takes n as a number of segments. Okay, so that defines the number of segments. That's a user-defined number. That's a user-defined value. Okay? And the way to do it is you create a linear space between A and B to define the intervals. And then you go over each interval and apply the midpoint rule or the left rule, okay? Or the right rule. All right, so go ahead and try it. You've got most of everything set up over here for you. All you have to do now is fill in the gaps, okay? And then we'll try to understand the code. Okay, go. You got 3 minutes. The keynote on my desktop didn't sync. So and it's changing a lot of things. Google Drive. It is open. Yeah. Didn't sync it. That's what's going on. Yeah. So once you are looping over the segments, you just apply any of the rules as usual. Okay? Hey guys, will you cluster in a group, please? I want you to work together as a group. Jordan, do you want to hang out with Michael and Maddie? You guys already have that figured out over here. Seiko, do you want to work with Eric or with Brandon here? Maybe. Yeah.
You haven't by chance figured out why my computer won't connect to the here, will you?
Oh, I haven't even thought about this. It's only here in
Like if I was to do this at home, it's fine. It just makes it hard to follow along when I can never run it.
That's ridiculous. So were you able to connect to CHPC notebook? The juno.chpc.utah.edu. So try that. Okay. So no progress here? Conrad, you got it? Okay. Yeah? Okay. Try it. Triad. Where we at? Need help? The for loop. What's with the for loop?
So we think this is what it should be for you.
Okay, so why did you specify 0 and 1 here? This should be A and B, right?
Oh,
Yeah? Okay. So how many points do you need for n segments? So think the segment has 2 points. Each segment has 2 points around it. So the total number of points is n plus 1, right? So with 3 points, you get 2 segments. With 4 points, you get 3 segments, right? So you need n plus 1 points.
Okay. But this is,
It's not that big of a deal, but it does change. And
right,
then,
it just changed, yeah.
but then now, what are you looping over? You have to loop over the segments, right? Not A to B. This will not work because this is not an integer range. So think about the range. You're looping over the segments from segment 0, segment 1, segment 2. That's how we count them, right? Segment 0, segment 1, segment 2. So where would be your starting point for the range? So this is just a counter, yes. That's a counter all the way to the last segment, which is, it's either n or n plus 1 or n minus 1. It's one of those, right? So count the segments. Okay, time. So who's got a solution for this? Conrad? No solution? Okay, you got a solution? It changes from the original value, but you got a solution. You have a solution. Okay, so let's work on this together. Yeah, so here's what I'm going to do now. We said we want to divide the A to B interval. We want to divide it into segments, okay, n segments, all right? Once we have those n segments, okay, what we need is the x values for those segments. And that's done in one shot with the linear space. So that gives us these points, x1, x2, x3, all the way to xn. Now we just loop over the segments. These segments, we call them segment 0, segment 1, segment 2, all the way to segment n. For each segment, all we have to do is know A and B locally for the segment, and f of A and f of B, and then we apply the formula. Okay, so let's see how this is done. Okay, so the first step, we'll start with the left rule, and then the same applies for the other rules as well. Okay, so I want to create a linear space from A to B, correct? So we're going to create all of these x values, all of the x values for the segments. But how many segments and how many points should we put? So if I want n segments, we need how many points? N plus 1 points. Because for 2 points, you get 1 segment. For 3 points, you get 2 segments. For 4 points, you get 3 segments, and so on, right? So we would put n plus 1 over here. Not that it's not going to make a difference, because if your loops are structured correctly, you'll be OK. But if you're in doubt, just print it out, OK? Rule number 1, OK? If you want to do from, let's say, from 0 to 1, 10 points, it gives you all of these points. So that gives you 10 points or 9 intervals. Interval from 0 to 0.1, interval from 0.1 to 0.2, and so on, OK? OK. Now, we declare our integration result. I call it result. We started off as 0. Because remember now we're going to fill in a rectangle in every segment and calculate the area of that rectangle and then add all of those areas up. So I need a variable to store the area, correct? I call that result, and I initialize it with 0. Why? Because I'm going to add to it. Initially, the area is 0. We don't know what the area is. We're going to make it 0, and then we'll keep adding values to it of the individual segments. Okay? Now we loop over the segments. This loop is just a counter, segment 0, segment 1, segment 2, all the way to the end, right? And in that loop, I need to access these x values, because these x values have become the a and b. So every segment now is its own interval with a and b, right? So I need access to those, and to access those, I need a counter because I'm accessing values in the array x, okay? That x array contains values x0, x1, and so on. So I need a counter over here, and this counter is a range variable. It goes from segment 0, because the first value is going to be x0, really, all the way to n minus 1. Now, again, this range variable, if you're confused about it, it goes from start to stop minus 1, okay? If you're confused about it, if you're in doubt, print it out, okay? Print I. So let's say it goes from 0 to 10. It's going to print 0 to 9, right? Okay. So now our range goes from 0 to n. Now for each segment, so the way you think of the loop, we start at 0. For segment 0, my A is x0, the first x, and my B is x at 1. In other words, the A is xi, and the B is xi plus 1. It's the next value in x, okay? So then B is xi plus 1. Now the result, what is it? Now in segment I need to apply the left rule. And what does the left rule say? It's b minus a times f, the value of the function at the left point, times f of a. So that calculates that little area on segment I, and then it keeps adding them up. Okay? Now the same thing applies for all the other functions. For the right rule, yes, Paul.
I was just trying to figure out the range part and where to stop. Because if you stopped at n, it wouldn't do n, right?
Yeah, it will. Of course, it will not. Remember, this is segment calculation, but it will go to x. So this will go to n minus 1, okay? But you can access xn over here.
So our last point
Is xn.
is xn, not xn plus.
No, it's xn. So you got n plus 1 points for n segments, right?
Yes.
So then the last one would be n minus 1 plus 1. It would be, xn. Yeah, it would be xn. So you get 0 to n for x, right? And that gives you n plus 1 points, right? 0 to n is n plus 1 items, right? But then that gives you n segments, okay? So the last entry here, the range, ends at n minus 1, okay? But then you access xn. That's the last value. Again, this range is the segment count. You're counting the segments, okay? Same thing here, except with the right rule, you get b minus a times f of b. And same thing here with the midpoint rule. The result is b minus a times f of a plus b over 2, okay? So now we call these functions, and this is what we get, like 1.272, 1.273. We're calling these rules with 200 segments here. You can do it with 10 segments if you want, or however many segments that you like. 20 segments, whoops. Now you can compare this with what I called to be the true value, which was 1.272, and we'll talk about errors later, okay? Okay, so now we started with the simplest approximation of a function. We approximated the function as a constant, which is a terrible approximation, but it's not that bad of an approximation if the interval is very small, because a function really, if you shrink the interval, if you zoom in at the function, for a certain range, it's pretty much constant, right? Unless you have strong variations, but you can keep zooming in more and more. So you put in more and more intervals. It's pretty neat what we're doing, really. We started with a very dumb approximation to a function, but then we applied it over many intervals, and that gave us a very decent approximation, okay? Okay, so now we can continue. Again, sorry, my slides did not update from what I had on my desktop, so I am going to be surprised by what's going to show up here, but though the slides, when they're uploaded, they will have the most recent content. Okay. Now, what about discrete data? So obviously, integrating an analytical function is all fun and interesting, right? But in practice, we're going to be dealing with discrete data. Again, you may be given, temperature versus concentration, or concentration versus temperature, or femur height versus, height versus femur length, etc. And you want to integrate those discrete data. So can we apply these methods to discrete data? Yeah, of course, absolutely. Okay, so let's see how. If you're given xi and yi values discretely over here, you use these rules exactly as they are proposed. For the left rule, you just apply it easily. Again, you count your segments, or you go over your segments, and then you just take the value at the left, right? So you're given x1 and y1, you're given x2 and y2, and so on, and you just simply calculate the rectangles based on the width of the left segment, the left height of the segment. Same thing with the right point rule. So notice this rectangle in the middle, how it changed, because we're using the right end height of the interval, right? Okay, but what about the midpoint rule? All right, groups, and you got 1 minute. Do you think we can apply the midpoint rule to these data, and when and why or why not? Okay. Are you all one group? Yeah, one group. Yeah, they abandoned you. You abandoned them, I feel. So this next activity, it's too bad sorry, I have you standing over here for nothing. I think next activity we try to record it. So think about the midpoint rule. It needs a value in the middle, right? It needs a value in the middle. Can you guarantee that you have a value in the middle with discrete data? So when you're given a continuous function, you can evaluate the function anywhere you want. But with discrete data, can you evaluate the discrete data anywhere you want? Okay, so I got yes and no's. All right, time. Okay, who thinks we can apply the midpoint rule for discrete data? Okay. Conrad, why?
Well, I mean, the same thing applies. So with a continuous function, we have 2 points. We find the median x value, the median y value. With discrete data, it's the same thing. I mean, it might not be consistent throughout all the data points, like the distances. I mean, we can still find an average.
So if you're finding an average, you're doing an approximation, and that approximation is not going to give you any more accuracy than there is, but it's certainly an option. Who says no, we cannot apply? Now you're changing your mind, Katrina. Yeah, so why not, Dylan?
Well, because they're discrete, you need to have a value for that.
In the middle,
point.
yeah.
The only way you can do that is if you interpolate it first.
That's what Conrad was saying. Okay, so both of you are talking about the same thing, but you answered kind of both questions. Now the rest of you, what's your answer? Like no or yes? Those who didn't raise their hands? No. Okay, so you can apply the midpoint rule. Okay, the problem with the midpoint rule is that you need a point in the middle. Okay? So if your data is equally spaced, okay, then you pick the point in the middle. But what if your data has an odd number of values or an even number of values? What do you do with the last interval? You start putting if statements, like if you don't have enough midpoints, you revert back to the left point rule, etc. Now, what if you're, yes, Eric?
Wait, so you're saying, like in this case, that x2 is the midpoint of x1 and x3?
Yes, because,
That's a midpoint between x1 and x2.
But how do you find the value at that midpoint? And how do you interpolate?
Well, you have an average value between x1 and x2.
Not necessarily. What if the data is changing, violently in between? So you're taking discrete data and you're doing one more approximation and then another approximation. Your best bet is not to use the midpoint rule. There's a better method to do this, and that's to automatically fit. We'll see it. It's called the trapezoidal rule. Will automatically fit a straight line. But so going back, if your data is equally spaced, use the midpoint rule. Skip every other interval and use the midpoint. You're going to get in trouble if you have an even number of points or an odd number of points. I don't know which one it is, but I wouldn't use the midpoint rule for discrete data. If you have unequally spaced data, then you're in trouble. Okay? Then you'd probably want to interpolate, but how can you justify that interpolation? Because an interpolation is not going to give you new information. You'll actually lose information about the data by doing interpolation. And we're already losing information by doing these numerical integrations. Okay? So don't do that. All right? Now, I'm going to give you a set of equally spaced data. And these data correspond to the metric tons of CO2 emissions per capita worldwide up to 2014, all the way from 1960. The data look like this. Okay. Again, on your activity 3 with your notebook, I want you to now implement the left point and right point rule now for a discrete set of data. Okay. Last we did it was for a continuous function where we artificially dissected the interval into as many intervals as we want. In this case, you have a predetermined set of intervals, okay? Now, all I want you to do is take those data, x and y, and add up all the little areas to compute the total emissions of CO2, okay? So go, you got 3 minutes. So typically when we're doing programming activity, there's not much noise going on. So,
Is there other type?
yeah. Hala, coming after. Yeah. Sorry, this is almost running out of battery. مش هيك 10%. يلا هلا next activity. Trapezoidal rule. I don't know. I feel. Yeah, it's too bad that I didn't think. Oh, crap! I am editing the integrated. I was editing the wrong one. Okay, so yeah. Okay, how we doing? You got it? Okay.
Numbers that are like 2 bigger than the ones that were already there.
Okay, we'll see now. Why don't you guys should the group. Okay, so you got it. Thank you. I think you got it. No, you didn't. Got a mistake. Get a mistake. Yes.
Because we don't understand what this means.
Pardon me?
We're having trouble because we don't understand what that means, like the colon and then how does that
You don't worry about this. All you have to worry about is xi and yi. Okay?
So then
Yep.
we should just be able to call it xi and yi.
Yeah, xi, yi. Yep. So all you have, that's all you got. Yeah. Yeah. So don't worry about the x and y data. You all worry about getting xi. You have xi and yi, okay? So xi and yi. All right. So who's got it? Who has something working? Conrad, Eric, Prasanna, Andy. Okay. Team back corner. All right. So what I'm doing here, I'm doing some Python jujitsu to import some data. You know, don't worry about that. These columns, essentially, the semicolon over here tells me to take the entire data in that row, and then, you know, I'm specifying the second index in the array. Don't worry about this. Know that xi and yi are given to you in this case, okay? Now, what I'm interested in is computing, going over these discrete data points and just computing the areas between in the segments, okay? So we're just gonna go over the segments until we run out of segments. In a way, this is much easier. This is easier than doing it with an analytical function, okay? Again, I'm gonna define my result of the integration to be 0, and I need the number of points, okay? Or in other words, the number of segments, but the number of points is easier to get. That's just the length of the array, okay? That's the length of the x data that you're given, or the length of y data, because they should be equal. And you can do error checking here, make sure that the length of x data is equal to the length of the y data, okay? So I get n, that gives me the number of points, right? And n minus 1 would be the number of segments, okay? Now loop over, let's say segments, it's a better word, and with that loop, what I'm going to do, we're going to go from 0, because we need to access x0 and x1, and all the way to what? n minus 1, n plus 1, or n. And y? One less than that. And then for our range function, it's going to go to n minus 2. But we're going to be accessing xi plus 1, so it will be n minus 1. So Conrad is right. Okay, who had n minus 1 there? Okay, good. Was it because it didn't work when you put in n? Okay. So, okay, now range, it's a little bit annoying to think about this, but let's go through it. Okay. So n, we called n the number of points in the array. So they go from x0 to xn minus 1. So our array goes from, so it's got, you know, it's got x0, x1, dot, 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 to xn minus 1. Those are n entries, okay? N entries for x. Now the range function goes from start to stop minus 1, okay? But I know that as I go through the intervals, I need to access xi and xi plus 1. So the highest value of I plus 1 I can get to is this guy. So I can at most go to xn minus 1, okay? Now here's how I conclude this. If I plus 1 is n minus 1, okay? So then n, oh, this doesn't make sense. Okay, never mind. Okay, so if I plus 1, the last value is n minus 1, then I need to go to n minus 2. The most I can go to is n minus 2. Because n minus 2 plus 1 will give you n minus 1, which would be the last value. So the last value I can assume is n minus 2. Actually, what I wrote was correct. So I plus 1 is n minus 1. Therefore, I is n minus 2. So that's the last value I can access over here, because I'm going to put xi plus 1 is equal to b. That's my b value. And xi plus 1 as the last value should be n minus 1. So at most, we can go to n minus 2. And therefore, range goes from 0 to n minus 1 because range goes from 0, from start to stop minus 1. Okay, then the rest is history. A is xi, and B is xi plus 1. And then f of A is what? Yi, correct. Okay? And same thing down for the right point rule. The range, again, goes from 0 to n minus 1. And A is xi, B is xi plus 1. Now, f of B is y, I plus 1. That's the value of y at point B. Okay? Now, when you do this, we can go ahead and apply the left rule and the right rule. They're quite close to each other. Okay? The true answer, I'll teach you about this function in a second, trap z, or the true answer with a very high degree of confidence, is, no, hold on, this doesn't make sense. This does not make sense at all. Okay. Nope, yi, I think I have to give it yi, yep, yi. Being embarrassed. Let you laugh at me. Okay. So it's somewhere in between. Okay, it's in between those two guys. Okay? Now we'll learn about this trapezoidal rule in a second. Okay, but first, maybe you can take a break now. 3 minutes. Okay? Go. All right. Do we have an answer? Nico, you got an answer?
Well, it's a trapezoid.
Yeah. Why?
You got distracted when someone asked me who I was.
Okay. So who are you?
Nico.
Maybe Eric can.
Because with the trapezoid rule, you can always have two points.
Yeah. Yep. Yeah, you don't have to worry about finding equally spaced points. I mean, the 3/8 rule requires, 4 points in an interval, and they have to be equally spaced. That's really annoying. So we stick with the trapezoid rule. That being said, and because of Eric, now you're going to have to implement the trapezoid rule for a discrete set of data. And that's your activity number 4. And apply it for the function we looked at in the beginning. This shouldn't take much time, because we know how to do this now for discrete data. So activity 4. Actually, no, for a continuous function. Sorry, you do this for a continuous function. And then we'll do it for discrete data. Sorry, that's this activity. Okay, so you're going to take a function f, an interval a, b, n number of segments, and then simply apply the trapezoid rule. You're Isabel, right? Yeah. Isabel. Gotta get you a name tag. How we doing, Storm Crows?
I was very confused because I'm like, 1 and 4, that's a terrible approximation. Then I realized it's the error.
It's a ratio. Oh, did I put there up there?
You made it so that
Oh yeah, that was a little bit extra work I was doing. Yeah.
that's a terrible approximation.
No, that's a ratio of errors, so it
No,
converges.
right, but when I saw
Yeah.
it first, I was like,
Yeah.
oh, that's not exact.
Yeah. So yeah, this is measuring the rate of convergence. So if you double the number of points, yeah. Katie, you having issues? Your code is having issues.
Yeah, I'm actually actually pretty good, but my code is having issues.
Okay, so we're looking at this one here.
Yeah.
Okay. Yeah, so there's nothing wrong with that. Print exact. So you got to call trap rule. So this is, okay, there's a mistake on the notebook. Okay, so you're probably seeing, please disregard these lines. I was experimenting with something as I was developing this notebook, but stick to this one, and then what you want to do is call trap rule on my function f from 0 to 1 with like 100 points, okay? So Katie, your code should run if you run that. Okay. See that smiley face? Okay. All right, so let's go ahead and do it. We did this. The linear space goes from A to B. How many points? If we want n segments, we want n plus 1 points. Then our range, as we count the segments, goes from 0 to n, okay? Because A is going to be xi, and the last value is going to be xn, so xi plus 1, right? And then that's what it is. So the trapezoidal rule already programmed that for you. And then if you call trap rule for trap rule f, yeah, okay, 1.272, etc. Okay, there's a function in NumPy called trapz. So np.trapz, my function from 0 to 1, and it didn't work. Okay, actually, nope, NP, so integrate. So trapz only works for discrete data, sorry. So integrate dot, let's see, trapz, my integrate dot quad, my f01, and that's a pretty good approximation. Okay, the last activity we will do is we're going to apply the trapezoidal rule for discrete data. Okay, so we applied it for a continuous function. Let's do it for discrete data. This should take no less than a minute, no more than a minute. No more than a minute. Okay, and you already have the pseudocode for that. And I call this trap rule, and it takes only xy discrete data. The key thing here is figuring out the range. And that range, if you copy from activity, what was it, 3, is the same thing as activity 3. Okay? So range goes from 0 to n minus 1, because you have n data points. So the last element in the array is xn minus 1. So your range needs to go at most to n minus 2, because I plus 1 needs at most to be n minus 1, okay? Katrina's like, whatever, whatever. Xi, and then so as you loop over the segments, A and B are xi plus 1. F of A is yi, and f of B is yi plus 1. And then your trapezoidal rule is this guy. And now we can apply this to the xi, yi data. So fa and fb. We can apply this to our data. Now we can call NumPy trapz, which I will cover in a second, yixi. We got the same thing, okay? Pretty much the same thing. Trapezoidal rule, NumPy trapezoidal rule. So you got one other way to verify. All right, so to wrap this up, I got a few more minutes. To wrap this up, next thing we're going to discuss are error bounds. The derivation of error bounds is very annoying, and it requires some background material. So we're going to go ahead and just show you the error bounds. The best we can do with these integration formulas is find the maximum error that we can commit using either methods, okay? And we have formulas for the midpoint, trapezoid, and Simpson's 1/3 rules. And I'm calling the error as capital E, and with a lowercase m for midpoint, T for trapezoid, and S for Simpson's. You'll see that all of those errors, there's a factor K, K, and M multiplying the interval, that's the full interval, B minus A, over the number of segments, okay? With the midpoint rule, you get K, B minus A cubed over 24n squared, okay? K is a constant that is related to the average second derivative along the interval. So if you look at the function, plot the second derivative across the entire interval, okay? If you take the average of that second derivative, that gives you an approximation for what K is. But that doesn't matter, because what we care about is really, what if you double the number for the same function and the same interval? So for the same function, K will be the same interval, B minus A will be the same. If you double the number of segments, what happens to the error? Does it get cut by half or by 1/4? Okay, so what this is telling us, if you double n, you cut the error by 1/4 rather than by 1/2. Okay, so that's very important. So that tells you how your method, what we call converges. We will learn this on Thursday when we do finite difference methods, okay? That has to do with the order of accuracy. We kind of alluded to this earlier with when we were doing errors in the first homework, second homework, when we computed the error ratio between two finite difference schemes. Okay. For the trapezoid rule, we got the similar bound, except we have 12 in the denominator. Now again, these numbers don't matter because it's the ratio of the errors that matter. If you double the number of segments, what happens to the error? It gets cut by 1/4, okay? Now let's look at Simpson's rule. You get n to the power 4, okay? So you get much more reduction in the error if you use the trapezoidal rule. But you will find that in practice, your error may be much smaller than this bound, because this is an upper bound, okay? And the last slide, of course, there are a lot of numerical packages in Python out there that do numerical integration, okay? We barely scratch the surface, all right? The two most popular are integrate.quad, which gives you numerical integration of continuous functions, and it takes the same form we used, same function signature, function name, and interval a and b. That's scipy.quad. It does adaptive quadrature, so it does some fancy stuff with, apply using Simpson's rules, Gaussian quadrature, etc. It's a little bit, we're not going to cover what goes in there, but it's a very reliable method. And for discrete data, I always use numpy.trapz, for the trapezoidal rule, okay? You can compare your results discretely to trapz or analytically to integrate.quad, okay? I will see you on Thursday. This finishes quadrature and numerical integration, okay? Thank you very much for coming in today.